All right, so my name is Tess, and I'm a software engineer here at Chain. And when we were talking about, sort of especially the technical talks that we could give tonight, we thought it would be a good idea to present something not only on the protocol side, but also on the systems side. So that is, we didn't want to talk just about contract design or cryptography or that kind of thing. We also wanted to talk about how we implement these ideas and build systems that are reliable and scalable and secure. So in talking about Ivy, Oleg covered a bit of the protocol side. And now I want to take you over to the system side and talk about Iago, which is our high availability data layer that lives inside each chain core. I'm pretty excited to share this with you tonight. I haven't talked about Iago very much, and also I wrote it, so I'm pretty excited to share this with you. And don't worry if you're not a systems programmer. I'm going to try to keep it pretty high level, so I hope anyone will be able to follow along. Okay, so at a high level, I want to talk about these things. First, I want to talk about network consensus and how that impacts our needs around a data layer. Then I'll talk about Postgres and how we chose it and how it replicates data. Next, I'll talk about this data layer itself, going a little bit into what happens when things go wrong. And finally, just for kicks, I want to tell you how we gave it its name. Okay, so let's talk first about network consensus and how that impacts our data layer. So this is a representation of a blockchain network. If you're here tonight, you've probably seen something like this before. Here are all these nodes, and they can communicate with each other, and that's wonderful. And usually, in the blockchain space, when we talk about distributed systems, we're talking about things at this level. We're talking about, fault tolerance and consensus, and we're talking about the overall network. But in a chain network, each node can contain a little distributed system. So let me show you how, and then I'll talk a little bit about why. So here's the anatomy. Here's our network, and here's the anatomy of a single node. So each node can have several servers running core D, which is our core daemon that runs all of the blockchain logic. And off to the side there, we have signer D, which is the signer daemon, which talks to the HSM, or hardware security module. And the HSM is responsible for securely generating and storing private keys, and signing blocks and transactions, things like that. Now, this section down towards the bottom is really the meat and potatoes of what I'm going to talk about tonight. Each server running core D talks to a fleet of replicated Postgres databases. So each of these sets of databases has exactly the same data shared across all of them. And now, you may be asking yourself, and pretty reasonably, why are we doing this? I can see you are shrugging at me right now. Why are we doing this? Bitcoin doesn't do this. Why should we? Well, great question, sir. In a lot of ways, this goes back to our consensus model. So we do build permission blockchains. So the version of the protocol that we're running right now has a consensus model that's really designed for that. And in this federated consensus model, there's three kinds of nodes. So first, a single node is the generator. And the generator is responsible for receiving transactions from the network, filtering out invalid transactions, and then periodically aggregating these transactions into blocks. It then sends these proposed blocks to the signer nodes. So then some number of nodes are signers, and this might include the generator itself. A generator node can also be a signer node. And these signers are responsible also for verifying that the block is valid, so all the transactions inside it are valid, but also for making sure that there isn't another conflicting block at the same height. So once it's validated these transactions, it will add its own signature to the block and then send that signed block back to the generator. And once the generator has a block that has received M of N signatures, it then publishes it to the network, where M and N are network level consensus parameters that can be configured on a network by network basis. So in this system, all of the other nodes are participants. That is to say, they can validate and verify transactions and blocks, but their approval isn't necessary for them to be published to the network. So to go back to our slightly corny blockchain diagram, you could visualize that like this, right? We have a single generator, a few signers, and the remaining nodes are participants. So this is pretty safe. It guarantees that we won't have conflicting blocks at a given height, assuming that no more than 2 m minus n minus 1 signers violate the protocol. And our protocol also supports consensus improvements, so we could implement a stronger consensus algorithm if we needed one moving forward. Okay, but all of this does rely on this assertion that the generator and at least m of those signer nodes have to stay online. So they must be robust and highly available. So that's why we have this system that looks like this, where we have multiple cores per node and multiple databases per core. It really is to ensure a very high level of availability. And then these databases collectively form the backbone. They're all running Postgres, and they form the backbone of our data layer. So to talk a little bit about Postgres, we chose Postgres as our database because it's reliable and well-established, and because a lot of engineers are familiar with it. And we also liked its replication features. So in Postgres, database transactions can be replicated both synchronously and asynchronously. And when I talk about transactions in this case, I'm not talking about blockchain transactions, I'm talking about database transactions. So not the exchange of value, but changes in state, right? And in synchronous replication, the primary won't commit transactions until the secondary has also received them and acknowledged them back to the primary. And in asynchronous replication, the primary will commit them as soon as it receives them, and then it will send them on to the secondary. So by default, Postgres replicates asynchronously. This is more performant, but there's also a higher risk of data loss because the primary might receive a transaction, commit it, and then crash before the secondary has actually committed it. So for our data layer, we want to combine these two replication modes. We want core D to write to a primary, which then in turn synchronously replicates to a secondary, which then asynchronously replicates to a tertiary. And we could call these databases A, B, and C, right? And if we wanted, we could also have database D that would asynchronously replicate from C. We could add E, which would asynchronously replicate from D. Now I'm forgetting the alphabet here. But basically, we could have a primary async rep and then a list of async reps, as many as we wanted. So if our primary A dies, we want core D to start writing to the sync rep B, which will then become the primary. C can then move up to become the new sync rep, and our imagined D and E nodes would continue to asynchronously replicate from their upstreams. If there are fewer than 3 live instances, this is considered a degraded state. This is a safe state. We're not going to lose data, if we're in this configuration. But if another peer were to go down, we wouldn't be able to recover. So, once we hit this point, this is really the point at which an operator needs to intervene. Okay, so to create a system that would behave this way, we wrote Iago. Iago uses an algorithm from Joyent's Manatee project, and this is the ASCII manatee that is at the top of Joyent's Manatee project. I personally am impressed by their attention to detail on that regard. And Manatee is a high availability Postgres project that uses Zookeeper and is written in Node. And my team really liked this algorithm, but we were a little bit less excited about operating Zookeeper or managing a service written in Node because we don't use those technologies for anything else. So I re-implemented the algorithm in Go and swapped out Zookeeper for etcd, and the resulting system is called Iago. If you're not familiar with etcd, it's a distributed key value store that uses Raft as its consensus algorithm. And Raft is supposed to be a more understandable version of Paxos, so Raft and etcd are not Byzantine fault tolerant. But again, that's okay in this case because it's completely internal to a single node. So each Iago peer contains 3 things. It's running a Postgres process and an etcd process, and then what we call the sitter daemon, which is responsible for knowing what this peer's role is and for promoting the peer if necessary. So in other words, the sitter daemon is what's executing that algorithm from Manatee that I mentioned earlier. Okay, so let's dig into this a little bit. When a new peer comes online, the first thing its sitter daemon does is register itself with etcd. So it creates this ephemeral representation of itself with a configurable timeout that is 4 seconds. And it refreshes that representation halfway through each timeout. So you can see it here, creating that representation, and then looping through in this go routine and just refreshing that halfway through the timeout. So the key thing to note here is that if this process goes offline, the ephemeral representation will disappear in etcd. So with that in mind, each node's ephemeral representation is watched by another node's sitter. So the primary is responsible for monitoring the sync rep and all of the async reps, or rather for watching their ephemeral representations in etcd. And then the sync rep monitors the primary. So everyone is being watched by somebody else. And if any of these nodes go offline, the monitoring sitter will take action to restore the entire system. And it does this by modifying this thing called cluster state. So the cluster state is a set of values stored in etcd, which means that everyone agrees on it, right? And it can only be updated by the primary or by the sync rep if it's about to become the primary. And every node in the system is constantly checking the cluster state in order to know their role in the system. So the cluster state includes these things. It includes unique identifiers for the primary, for the sync rep, and for every async rep. It also includes an integer representing the generation. And so if a peer, what that means is if a peer changes the cluster state, it also increments that generation. So this helps prevent collisions. Lastly, the position of the write-ahead log is also stored in cluster state. And that can be used to prevent data loss in certain kind of edge casey failure conditions. And I'm just not going to go into that tonight. Okay, but let's dig into this monitoring business. So this is sort of a shored up version of the monitoring loop that the sync rep runs. So when it runs this loop, it's checking for 3 things. First, it's checking that the primary is still online. So there it is watching that ephemeral representation in etcd that represents the primary. And if it notices that the primary has gone offline, it will go ahead and promote itself to primary. Second, it's watching for a change in generation. So like I said, if any node updates the cluster state, they increment the generation. So if the generation has changed, that means that something in the system has changed, and this node needs to check its own role again. And then finally, in this loop, it's running a health check on its own Postgres process. So if this peer's Postgres process fails, it will take itself offline in order to signal to the primary that it needs to promote a new sync rep. Okay, so let's look at that in action. So what happens when something goes wrong? So if the primary goes offline, the first thing that will happen is that the primary's ephemeral representation will expire, right? And then the sync rep will notice this, and then it will take action to declare itself primary. So first, it will promote its own Postgres process. So it reconfigures Postgres so that it's accepting writes from core D rather than replicating from an upstream database. And then it will rewrite cluster state so that it is the primary, and the first async rep is listed as the sync rep, and the generation counter has increased. So now we're in this situation at this point where the cluster state has changed, and it's time for the other nodes to notice what's happened. So the old first async rep will notice that the generation has changed, and it will check for its new role. It will realize it's now sync rep and change its Postgres configuration to replicate synchronously from the new primary. So once that whole song and dance is done, we end up with a system that looks like this, which again is basically that safe state that we were hoping for. Safe state we were hoping for if we have to fail over. Let's talk about a slightly hairier failure situation. So what happens if the sync rep goes offline briefly and then returns? So just in the previous scenario, the first thing that will happen is that one of these ephemeral representations will expire. And in this case, the primary will notice that the sync rep's ephemeral representation has expired because it's the one monitoring it. And it will promote a new sync rep. So it will update cluster state, move in a new sync rep, and significantly, it will increment the generation. So then let's say the sync rep, the old sync rep, comes back online and it attempts to update the state because it's confused. It thinks the primary has gone offline. But it won't be able to because the generation has changed under its feet. So instead, it will reset itself and come back online as an async rep at the end of that line of asyncs. So the old async rep, and then we sort of fall back into this thing where every node notices something has changed and they put themselves in the right place. So the old async rep will now notice that the generation has changed. It will check for its new role, realize its sync rep, and reconfigure its Postgres process. So again, even with a failure and then some sort of like funny business from one of the nodes, we still end up in this safe state. So I do want to take a step back and point out how Iago looks from the perspective of Core D. When Core D goes to query this data layer, it doesn't have to step through a complex web of Iago logic. In fact, it actually doesn't touch the sitter program at all. It simply on startup asks etcd for the IP address of the current primary, and then it queries that process directly. And if it ever can't reach the process, it just asks etcd again, hey, who's the latest primary? And it keeps querying Postgres directly. So the interface from Core D's perspective is actually quite simple. So finally, as promised, I wanted to share why I named this project Iago. Obviously, the most important consideration when naming a Go project is that it has the word Go somewhere in the name. I think that's the rule, right? I also liked Iago because it's pretty short, and because Iago is a Shakespearean character in Othello who runs around like lying to every other character and just creating chaos through this strategy. And our Iago is supposed to do the exact opposite of that. It's supposed to tell every other node in the system the same thing and create harmony and truth. So it's sort of an aspirationally ironic name for this system. So that's all I have. If you have questions, I'll be hanging around a little longer. I'm _Tess on Twitter. And before I close, I also do want to plug, once again, I realize everyone tonight has now plugged these sort of community groups. But we do have a community Slack that is, reasonably lively, and some support forums. So if you have ongoing questions, those are two great ways to get a hold of us. Thank you all so much for coming. We'll all be around for a little bit longer, so please come ask questions, and thanks again.